Everyone, welcome back, and today let's solve Leetcode problem 2353 titled Design a Food Rating System. So we have quite a long problem statement here. I'm not going to get into this entire explanation here, just to kind of quickly summarize what this problem statement is really saying. Effectively, we have to support initializing a set of foods where each has a cuisine and a rating. We also have to be able to update a food's rating and return the highest rated food for any given cuisine, right? If it's a tie between the highest rated foods, we'd have to return the lexicographically smallest name, right, based on the, of course, characters that those food names are actually made of, right? All right, so let's go ahead and get into the examples here and see what it really means here. In example one, we're basically having these separate methods, food ratings. We have highest rated, we have highest rated, we have change rating, right? Basically what this is saying is food ratings is our object of the class, and these are just callings or when instances that we call these methods here of highest rated and change rating. And these are effectively the outputs when we actually call those methods based on if we actually return the, or rather update a food's rating, or we return the highest rated food for that given cuisine, right? And as you can see, the output is going to be correspondingly the same thing. Of course, it's always going to be null for when we're calling this change rating method, because it's going to have a void return type. It's really just updating a food's rating. We're not actually returning anything. That's also something to look out for. The only thing that actually returns anything is this highest rated returning method here, which actually does return the highest rated food for that given cuisine parameter, right? So that's basically it for the explanation here. For the constraints here, we see that n is going to be the length of our foods, cuisines, and ratings, and it's going to be between 1 and 2 times 10 to the 4th power, where any value in foods and cuisines are going to be between 1 and 10, and foods and cuisines at any index I are only going to be lowercase English letters, kind of just confirming what the problem statement said, and just a few more kind of constraints here that you guys can read on your own. It's really just make sure that the problem is always going to be valid, and we're not going to have any really weird edge cases that we have to worry about in our code. Which brings us to how we actually solve this problem. On a high level, how are we really going to solve this problem? Basically, we're going to be using 3 different mappings, right? We're going to have a food to rating mapping. So basically, we're going to be given a food name, and it's going to map to its current rating for fast lookup and fast updating for our change rating updating method. And we're also going to have a food to cuisine method, or mapping, if you will, where we're given a food name and it maps to its corresponding cuisine for us to be able to actually know which cuisine and which cuisine heap to update. And finally, quite intuitively, we're going to have a cuisine to heap mapping. Basically, for each cuisine, we're going to have a heap or a priority queue that stores entries that allows us to actually quickly get the top food for that specific cuisine parameter, right? So effectively, how is this going to actually work? Basically, for the actual heap entry format here, it's going to take in a parameter or tuple of length 2. It's going to have a negative rating, and it's going to have a name, right? And the reason why we want the negative rating is because by default, heaps or priority queues in Python are always going to be minimum heaps. And so since we want to return the largest rating from our return method or highest rated method here, we want to return the largest rating, we have to then sort them by their negative rating so that the largest ratings are actually going to be at the very top of the stack because of that minimum heap default property. And of course, for ties, we also have to return the lexicographically smallest name because the tuple is going to compare the second element when the first elements are equal, right? Kind of just handling that case in the tuples as well, which leads us to the main observation that we have to make to be able to solve this problem in this format as well. Basically, removing any arbitrary items from a heap is very costly. More specifically, it's going to be big O of n. How do we kind of find an alternative for that? Well, that's how we're solving this problem. We're going to be using something called lazy updates, is like how I like to call that. Basically, whenever we actually change a rating, we're going to have to push a new tuple of length 2, negative rating comma name, into that cuisine's heap. Basically, again, that's going to be that length of 2 tuple for that specific cuisine's heap without actually deleting the old tuple. And so when actually querying the top, we simply just pop the invalid or the stale entries, if you will, until we actually find one that matches the current rating in the food to rating map. Right? Basically, that's going to give us the change rating as a big O of log n push, a lot lot faster and more efficient than big O of n, and the highest rated will be amortized to big O of log n, because each stale entry, if you will, is going to be popped at most once overall, which brings us to the main coding part of this solution, which I think will make a lot more sense once we actually get into each individual method and how it works in nature here. Right, so the first thing that we're going to do is actually initialize all our variables, and that's going to be in this init constructor here for our object using the self keyword in Python, right? In other languages like Java or C++, it would be this, but in this case in Python, it's simply just self, right? Not really much of a difference. You can think of them as essentially the same, self and this, at least in this case, right? So self dot, and I'm going to call it food to rating. Again, keep in mind this is the first of our 3 mappings here, and it's going to be a map. So you guessed it, it's going to be the form of a hash map or a dictionary in Python, right? And the whole point, again, of this food to rating hash map here, basically it's going to map each food to its current integer rating. And we're going to update this on the change rating method, and we're going to read it when we actually validate our heap entries, or our heap inputs, if you will. Now, what was the second kind of mapping that we talked about, or dictionary that we talked about? Well, it would be the food to cuisine hash map, and that's also of course going to be initialized to an empty hash map. I really do hope I spelled cuisine correctly. I'm not completely sure. I think it should be right. Cuisine, yeah, that's right. And finally, for our final mapping, it's going to be the cuisine to heap. Yeah, I'm very scared of my spelling for cuisine here. I feel like I'm going to misspell it any time in this video here. And in this case, we're actually going to initialize it not to a regular hash map, but a empty default dictionary, right? And of course, our base parameter or our data type for all of the keys are going to be in the form of a list, right? Basically, this whole point of this default cuisine to heap, as the name kind of suggests, is that each cuisine is going to map to, in this case, a list, hence why we have a list parameter data type passed into this as the parameter of this default dictionary, and it's going to be where each cuisine is going to map to that list, and we're going to use a heap with the heap queue module, and each heap is going to store, again, that length of 2 tuple containing the negative rating with its corresponding food, right? And again, keep in mind it has to be negative rating, because since by default minimum heaps or priority queues in Python are stored by their smallest value or minimum heap, making all the values negative is going to store the largest value originally at the top of the minimum heap. And so when we pop it off, we simply have to make it negative again to get its positive or absolute value, right? And now we have to actually start with this main logic, if you will, of this initial method here. So once we've actually initialized the 3 mappings or heap data structure, or rather not data structure, heap data structures, but hash map data structures here, now we have to actually start iterating through our 3 input lists. And since we know we're going to have kind of lengths of 3 in this case, what I'm going to do is use 3 parameters, right? Because we're going to considering 3 different variables at once. And it's going to be the food name, the cuisine, and the rating for that food, right? Those are kind of our 3 variables or iterators that we need to take care of and consider when iterating over our input here, right? Or our 3 input lists, if you will. And so I'm going to say for every F or food name, C or cuisine, or R and R or rating I'm going to use something called zip in Python to be able to iterate through these 3 lists concurrently. And I'm going to actually pass in the 3 lists that I want to iterate through concurrently, which again would be the 3 input lists: food, cuisines, and ratings. I think it's plural, right? It should be plural. Yeah, I think it's plural. Yeah, okay, anyways. Foods, cuisines, and ratings, right? Effectively, again, we're iterating through our original 3 input lists in lockstep, where F is equal to food name, C is equal to cuisine, and R is equal to rating for that specific food, where we're initializing our structures for each food as we iterate through them. And so in that case, because of that, for every iteration in this solution here, or rather, for every iteration in this method here, what I'm going to first do is get self.food to rating here for our first mapping for this specific food, and we're going to set the index at F to be our current rating R, right? Effectively, we're storing the current rating for this food F, or rather this food name F, in the food to rating dictionary. So basically, for this key food or food name, it's going to be equal to this rating R that we see in this iteration to whatever values F and C and R actually are in this specific iteration of this for loop here. Very similarly here, in this case, just a different mapping here, it's going to be the food to cuisine And it's going to still be at the same food name F, but in this case, instead of R, it's going to be C, the actual cuisine itself. We're storing the cuisine of F in the food to cuisine dictionary, or food to cuisine mapping, keyword mapping there. And finally, for our final kind of mapping, and that's going to be the more complex one, at least relatively, the self cuisine to heap, right? And the way this is going to work is we're going to, again, be using heap q. So heap q.heap push. This is basically an operation provided by the heapq module, and we're going to push onto the self.cuisine to help data structure. So basically the first parameter is simply just going to be the actual data structure or heap that we're pushing onto, and the second parameter is what we're actually pushing onto this heap, which in this case would actually be, again, that length of 2 tuple kind of parentheses, which would have the rating, and it would also have the food name, right? So it's going to be -r, and it's going to be F, right? -r again. Why? Because it's going to let the min heap behave as a maximum heap, where we're actually storing the largest food rating at the top of the list because of its negative value property, right? And we're basically just pushing the tuple -r, comma F into that heap for the cuisine C, and basically that F is also going to ensure that the lexicographic tie breaking is going to happen automatically when popping off the highest rated value or food name or cuisine in the change, or rather in the highest rated method here, right? And believe it or not, that's really actually it for the initial constructor or init method here. Now we have to move on to the change rating method, which is going to be relatively short, right? It's really just 3 lines, really just kind of looking up where the food belongs to and actually just updating its value, right? This is what's going to return null or none in Python. This is just the updating method as by itself, right? And the way this is going to work is we're going to get the cuisine, and it's going to be self.food to cuisine, simply just accessing the food to cuisine mapping at that specific food, where food is simply just going to be nothing but our parameter. We're simply just looking up which cuisine that this specific food input, our parameter, actually belongs to, because we need this to actually decide which cuisine heap to update, aka this one, whatever it maps to, right? Once we get this, we're going to get self.food to rating at this food and set it to be equal to the new rating, which is again a new parameter, or which is again the second parameter or second input in this method here. We're simply updating the food to rating mapping to reflect this new rating for that specific food name, where it basically makes the authoritative source of truth for any food's rating at that current moment, right? And I don't know if I pronounced authoritative correctly. I think I pronounced it correctly just now. Effectively, it's going to make that authoritative source of truth for any food's current rating, right? That's what this assignment is doing. We're simply just updating the food, all of the food's old rating to this new rating using this authoritative source. And I misspelled it or mispronounced it once again. Now, the final operation, again, is still going to be a heap operation where we actually push this new rating for this specific food onto the actual appropriate cuisine heap, right? Because, of course, we have to update it there as well for the new rating. So heap q.heap push, still the same operation. And again, the first parameter is always the initial data structure that we're pushing onto, or in this case, the heap that we're appending to, and that's going to be self.cuisine to food at this cuisine itself. And our second parameter is the actual tuple, again, of length 2, the new rating and the food itself, or rather the food name itself, if you will. Which brings us to, or rather, let me just quickly kind of explain what this kind of a line of code does. Effectively, we're just pushing the new tuple, new rating and food into that corresponding appropriate cuisine heap, and we're not attempting to remove the old tuple. That's kind of the key observation or key takeaway to remove from this piece. We're simply relying on that, again, lazy cleaning during the highest rated. Instead of having to actually also remove the old tuple, we're simply adding on this new one instead. Right? And once we finish that, now we're on to the last method here, which would actually be the highest rated method. Also, I think the longest method as well, but it isn't too difficult to explain it in nature. It's just kind of the logic behind it. So let's first get a reference to the heap list for this specific cuisine parameter. And so I'm just going to call it heap, and it's going to be self.cuisine to heap. Oops. And we're going to pass in for the parameter the current cuisine parameter, or the current cuisine input. We're simply getting a reference to the heap list for the cuisine. Basically, it's where the entries actually live. Now, while this heap is non-null, meaning while the heap still has entries, within this loop we're going to actually check if the top entry is valid, meaning if it actually matches the current rating. And if it doesn't, then we have to then pop it because we have to pop the stale entries, right? So while the heap is non-null, while we still have entries to deal with, we'll get the rating, and we'll have to make it negative because we want the largest rating in the form of a positive value, and we'll get the food name, popping it off from heap at index 0, which is again going to be storing that on the top, the largest rating, right? Effectively, the peak is at the root of the heap, right? That's going to be at index 0, and we basically have to just pop it off, rather peak at the root without actually popping it off. And again, rating as that underscore negative is basically that stored negative rating, where name is the food name itself, right? We're simply peeking at it, by accessing heap at index 0, which is the largest rating, but we're not actually popping it off quite yet. Now, the current rating is going to be self.food to rating. That's where we access it, and it's going to be at this specific name. We're simply, again, looking up that authoritative current rating for name from that food to rating dictionary, or again, keyword food to rating mapping, right? And once we actually get that authoritative current rating for this specific name, or food name, if you will, now we have to then check if it's actually stored in the heap, and if it actually does equal the current rating. So if, now we have to make this negative rating, so rating at negative, if that's equal to the current rating, basically, again, we're checking whether the rating stored in the heap, basically the negation of the rating neg to make it positive, if it actually equals the current rating. And if they match, then we know that this heap entry is actually valid, meaning it isn't a stale entry. And so if that's the case, we simply just return the name. And we return the name because that means that this top entry is valid. We have to return the food name immediately because that's going to be the highest rated food for the cuisine, because the tie is broken automatically by the lexicographic order because of how the tuples are ordered in nature, right? So that's really kind of like the quick, simple case where we don't have to worry too much about it. We can just immediately return the name, right? And effectively, in every iteration, if we don't return the name, we're simply just going to add to the heap queue, or rather pop from the heap queue, so heap queue.heap_pop. And in this case, the only thing that we have to pass in is which data structure that we're actually popping, because by default, it's going to pop the topmost data structure. And so the way we're going to do that is basically just pop off from the heap, right? If the top entry was actually stale, meaning it didn't match our current rating, we didn't immediately return the name, we'd have to pop it and continue the loop to examine the next candidate, if you will. That's how we lazily clean the heap. That is the main logic behind this solution. And effectively, finally, if we never return named, if we never actually found a valid kind of rating or highest rated cuisine or food in this while loop here, once the while loop is done executing, once it fully exits, we have to simply return an empty string. That basically indicates, or it's kind of like our defensive fallback that returns that empty string, because it indicates that we didn't actually find any valid entries. Now, according to the problem constraints, it does say that there will always be at least one food for any specific queried cuisine. So technically, in nature, this should never actually happen. We should never actually reach this line when actually executing this code, but I just do it for best practice and just in case, because you never really know, right? So unless I made any syntax errors here, there should be accepted and there should be a valid solution. So let's go ahead and verify that. Okay, so let's go ahead and see what I did wrong here. Heap queue.heap push. Cuisine, I probably spelled it wrong. I knew this was going to happen here. Yeah, this should be heap. I have no clue why I spelled help. That was quite hilarious, but now this should be accepted, and now this should be a valid solution. So let's go ahead and see what's the issue here. Cuisine to heap at C. Okay, let me go ahead and quickly run this to see what the actual error is, and then we can kind of debug from there. Cuisine to food. Okay, so this should be cuisine to heap. Again, very simple, like spelling errors, or just using the entirely wrong word completely. Things like that. That always costs me. But now, as you can see, this really is just about as efficient as you can get it to be. So again, On a high level, how are we really solving this problem? How does it really work all together? Basically, on initialization, we're simply storing for each food its rating and its cuisine, and we're pushing one tuple of length to its rating and its name, and of course the rating has to be negative to actually store the highest or largest value to the corresponding cuisine heap. And that heap is basically just letting us ask what actually looks at the top for this cuisine, right? And when we actually call the change rating method here for the food and new rating parameters, we're basically updating that, again, authoritative rating map of food to rating at that food and setting it equal to the new rating parameter or input. And then we're pushing the new rating and food tuple of length 2 to that specific cuisine's heap, where the old tuples for that same food would simply just remain at the heap, but then would become stale because of that new addition or update, if you will. And effectively, when we're finally calling that last method here, the highest rated cuisine method, basically we're repeatedly peaking at the heap root and then comparing that stored rating to be the authoritative food rating for that name. And if they actually match, then the root would be correct and it would return its name. But if they don't match, the root would be stale and we'd have to pop it and continue, where each stale tuple would be popped at most once across the runtime of this entire solution. And so that lazy cleanup is still quite efficient in most, standard average cases. Right? And to kind of repeat how that peaking part kind of works, effectively in this highest rated cuisine method, we're simply repeatedly peaking at the heap root, and we're comparing the stored rating there to the authoritative food to rating kind of value for that specific food name. Right? So again, tying back to that main observation that we really could make, basically lazy deletion would trade an occasional extra pop during a query for a lot much more faster updates, where we would actually completely avoid linear time removal. And in many problems where updates are frequent but deletions are quite rare, basically like this one, lazy approaches are a lot simpler in terms of just simplifying code and also improving the average performance of our solution as well, right? And that another observation is that tuple ordering of negative rating and name kind of does double duty. It not only gives priority to larger ratings because of that negative rating, it also automatically enforces that lexicographic tie breaking because of that name part, right? That kind of saves any extra checks, and because we're also passing a name as a second parameter, it's automatically sorting it by lexicographic order to account for that tie-breaking property that the problem says as well. Which brings us to the complexities of this solution, right? So it's quite complex here. But the overall runtime complexity is going to be big O of n log n. Right? And the reason why is because we're pushing n items into the heaps, and we're also doing a dictionary, but that's all going to be big O of 1, and the heap push itself is big O of log m, and m is going to be the number of items in that cuisine heap, which is log n typically. Right? And now the highest rated kind of call here is going to be big O of log n fully simplified, where each invalid heap entry or stale entry would be popped once in total over lifetime. And so although one call could technically pop many stale entries across most of our operations, each stale entry would add one big O of log n pop in total, right? In worst case, a single call of that highest rated method would cost big O of k log n if there were k stale entries that would be removed during that call, but those entries really wouldn't be removed again anytime later, right? And for the actual memory complexity here, it's quite simple. It's really just big O of n plus the number of updates, right? N plus the number of updates, sorry. Right? And n is simply just going to be our actual entries, or n entries, and the number of updates, quite simply, is just the actual number of updates that we do or calls that we do of this change rating method, how many times we actually call it, right? So to kind of summarize, the memory complexity is big O of n plus the number of updates, and the runtime complexity is going to be big O of n log n. Right? N is going to be the number of foods, and Q is going to be the number of operations, which is basically just be the sum of the number of updates and queries, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.